ITC lunch of the academic year, so we will not have one next week. After next week, we have the Sackler conference on transients. All are welcome to attend that. We just had an excellent ITC colloquium by Joan Schmelz, who is sitting over there, and we will hear more from her in a few minutes. Our first speaker is Zach Slepian, and before I introduce all the speakers today, I just want to mention that he is the recipient of the Keto Prize that we award once a year to the best PhD thesis in theoretical astrophysics. And I just wanted Eric to say a few words. This prize was established based on a donation, and the fundraising campaign needed for that prize was the shortest I ever encountered. It was half an hour. We discussed the need for such a prize at the meeting of the senior faculty of the ITC, and then when we left the room, Eric suggested that, to establish the prize based on his own donation. Wanted to take this opportunity and thank him for doing that, and ask him to say a few words about the rationale for that prize.
Oh, right now. Oh, sorry, I was waiting for the talk. Well, historically, there was a fireman prize, which has been traditionally given to the best observational PhD thesis at Harvard. And so at the ITC, we thought we should have a similar prize for the theoreticians who aren't eligible for the fireman prize. And so that's what we did. We set it up. And this year it was won by Zach. And as I understand it, the rationale was that although the comparison to the development of the fast Fourier transform and the speed of computational ability, there wasn't exactly a direct comparison, but it did come up in the conversation. And so the idea is that one can now calculate the 3-point correlation function in the same speed as the 2-point correlation function. And this simplifies and allows a lot of this kind of analysis. So we'll look forward to hearing about it from the person who knows about it.
So this is a new tradition that we have, that from now on, whenever the Keto Prize recipient is selected, we will have that person present a brief 10-minute talk where we can grill him or her on the science involved. So Zach will talk about revitalizing the 3-point correlation function of Galaxies to sharpen the Baryon acoustic oscillation standard ruler. And after that, we'll hear from Joan Schmelz, who is visiting us. And she will talk about new results from the Arecibo Observatory, where she serves as the deputy director. Then we'll hear from our CFA colloquium speaker and the Cecilia Payne-Kopashkin Prize lecturer, Sara Seager from MIT, who is a former graduate student from our department. We are extremely proud of her accomplishments since then. So I should say that most of her best work was done after that. She will talk about a new, very ambitious mission that is likely to reshape the way we think about planets and other stars. It's Starshade to Rendezvous with the WFIRST AFTA mission. And finally, we'll hear from Merav who's a professor at Boston University. Merav Opher. And she will talk about the Heliosphere Revisited, Heliospheric Jets, Reconnection, hotspots, and their impact on the large-scale draping of the interstellar magnetic field. We'll start with Zach.
Okay, thank you, Avi, and thank you, Eric, for saying some words that I think were actually a good summary of some of the stuff I won't, unfortunately, have time to tell you about. So I'd like to thank Eric for his generosity in endowing this prize, and I'd also like to thank Avi and the other ITC members, in particular Doug Finkbeiner, Daniel Eisenstein, and Ramesh Narayan, for serving on my thesis committee. Now, Avi actually had to be out of town for my thesis defense because he was wooing an even bigger source of funding, a billionaire in California. So I think the reason he made me win this prize and give the talk is so he can now grill me on it. But I also want to say, I've given several other talks in front of Avi at the ITC and other places, and I've always worn a sports coat, and Avi always asks me, Zach, why are you dressed so nicely? Are you getting married? So the first couple times I wasn't quite sure what to say. The last time I said I'm married to my work, and I guess if I'm married to my work, this is now the child that Avi is witnessing the birth of. So with that said, I'll tell you about revitalizing the three-point correlation function of galaxies to sharpen the BAO standard ruler. So the big picture is dark energy. Dark energy drives accelerated expansion of the universe. It's 71% of the current energy density, roughly. We're 5%, and not just us, but all baryons, although after lunch, maybe that fraction will go up. And dark matter is 24%. So this is not a picture of dark energy. This is a picture of a lake at sunset. But I think you need to look at something when you think about dark energy. And like the lake at sunset, dark energy is basically homogeneous throughout space. We think it doesn't really have any perturbations, and it fills all of space. And it's actually created, as far as we know, as space expands. So that's one aspect of why it can drive accelerated expansion. So measuring the expansion rate of the universe actually allows us to constrain dark energy. So one of the most important techniques for doing that is the Baryon acoustic oscillation method, which was developed by Daniel Eisenstein here at the CFA, as well as a large team with the Sloan Digital Sky Survey and theorists elsewhere as well. So what this technique does is it compares the imprint of fluctuations at recombination when the CMB forms at redshift roughly 1100 with the late time clustering of galaxies, which I'm just showing in a redshift slice here. So the CMB formed 14 billion years ago when the universe became neutral. Prior to that, the baryons and photons were tightly coupled by Thomson scattering. And so you had these degree angular scale hot and cold spots. Now this is of course showing you the anisotropies, which are 1 part in 10 to the 5. If you just showed the background, you wouldn't be able to see anything. So this is only 380,000 years after the Big Bang. But then the galaxies we observe are roughly 7 billion years ago at redshift 1 to today at redshift 0. And the idea is this pattern of angular clustering actually imprints on the late time clustering of the galaxies. And so by measuring both, we can actually infer how much the universe has stretched in the intervening time. So this is shown with these two rulers. One of them is bigger because the universe has stretched. And the point is that dark energy is one of the forces that drives this stretching. So by measuring the stretching in different redshift slices, so at different times, you can learn about dark energy. So the BAO method has been used with extreme success in the two-point correlation function, or 2PCF of galaxies. This takes pairs of galaxies and asks what is the excess of pairs over random. So on the x-axis here, I've plotted just the separation in co-moving h inverse megaparsecs. H is just 0.7 roughly. And on the y-axis, I've just plotted the separation squared times the correlation function. So again, this correlation function measures excess above random. So these are actually extra pairs of galaxies that you would not see if the universe was a purely random field of galaxies. And the interesting thing about this is that you have this very distinctive bump, which I've marked with this black line, that occurs at about 100 h inverse megaparsecs. These DRs are just showing you different data releases of the Sloan Digital Sky Survey. I think the key point is that the error bars have shrunk a lot. You can see DR9 has error bars that are roughly a factor of 2 or 3 bigger than DR10 and 11. So the precision of this technique has really improved in the last decade, and it's now giving us 1% constraints on the cosmic distance scale. And the way this works is that we use this bump here in the two-point correlation function as the standard ruler. You look for this bump in different redshift slices, you figure out what physical scale that corresponds to, and that tells you the size of the universe at those different redshifts. I should also mention Daniel Eisenstein was actually one of the first two groups to detect the BAO bump in a sample of 46,000 luminous red galaxies from SDSS DR6. Sean Cole and his team in England detected it at around the same time using 2D FGRS, and this figure is from just the latest BAO data paper, Anderson et al. So the question I became interested in asking in my research was, why not use triplets of galaxies to do the same thing? One can measure the three-point correlation function, which just measures excess triangles over random. And it seemed to me that there should be BAO features in that as well that could be used as a standard distance ruler. So I'll show you that in just a second. But first, we have to go over some notation to understand the three-point function. The two-point function is simple. It's just about lines, the distance between 2 points. But triangles are much more complicated. Instead of just having a length, they have 3 parameters. There are different ways to do this, but here we're going to be looking at triangles as a function of the opening angle, theta 1, 2, and the length of these 2 sides enclosing it, R1 and R2. And the idea is you just have 3 galaxies, Galaxy 1, Galaxy 2, and Galaxy 3. And you count how many triangles are formed by the different triplets of galaxies, and you plot the number of excess triangles above random. So there's one extra step here. What we've done is actually decomposed the 3-point correlation function, which, as I said, is a function of these 2 side lengths and the angle. We've decomposed this into a factorized form where the radial dependence is given by these zeta L coefficients, and the angular dependence on powers of cosine theta is given by Legendre polynomials. So these PL are Legendre polynomials. They're just deterministic functions, and it's actually the case that this is a complete basis. In other words, any function of R1, R2, and cosine theta can be decomposed in this way. You might need to go to an infinite sum over the L's. In practice, we end up not needing that, which is good. So these panels are the types of things that I'll show you a bit. Basically, this is showing at one fixed L, this happens to be the dipole, so just the cosine theta dependence. This shows you the excess of triangles as a function of side length 1 and side length 2. So red represents an excess of triangles, and blue represents a deficit of triangles in this plot. And again, the color, the intensity of the color represents the number of triangles with these given side lengths. And again, we've projected the angle dependence onto the Legendre polynomial. So there are BAO in the 3-point function exactly as I had hoped. This is again showing you a blow-up of the dipole moment of the 3-point function. And this turnover from red to blue at 100 H inverse megaparsecs is due to the BAO. There's one here as well. This plot is symmetric by construction because triangles don't care whether you label one side R1 or the other side R1. Now what's interesting is also there's actually a BAO feature here, which I've highlighted in this box. And this is harder to see, but it's basically this white coming in rather than the red over here and the blue over here. And basically this is a crease. And so you should really be thinking of the BAO as generating these features by just taking a square sheet of 8.5 by 8.5 paper and marking points halfway around each side and then making all of the possible creases in that paper. So you can make vertical creases, you can make horizontal creases, but you can also make diagonal creases. And this feature is actually also caused by the BAO, as is this one and this one. So we don't use these because they're at large enough scales that the clustering of galaxies is very weak and the error bars are not favorable. But certainly this aspect of this plot is quite interesting observationally. So the goal is now to use the BAO method in the 3-point function to measure the cosmic expansion rate. So I'll just tell you briefly about the sample we used to do this and then show you the results. So the sample is the CMAS sample of the Sloan Digital Sky Survey, data release 12. It comprises 770,202 luminous red galaxies. They have roughly constant stellar mass. That's how they're selected. And they're in the redshift range 0.43 to 0.7 with an average redshift of 0.57. This is done using the 2.5 meter Sloan telescope in New Mexico. So one more slide before I show you results. This is just a BAO primer introducing you to 2 ideas about how we analyze the BAO. So one idea is that you can look at a no-wiggle model. So this model is a model where the large-scale growth of perturbations is correct, which is actually suppressed relative to pure cold-dark matter for more technical reasons. But these no-wiggle models have no BAO. So here I'm showing you the Green's function. The Green's function is the response to an initial point-like overdensity. If you just put a delta function over density at redshift infinity, this is the late time distribution of matter around it. So you can see this no wiggle just has a kind of smoosh over here. We've weighted it by r squared so you can see more. That's why the smoosh doesn't appear right at the origin. But it's really quite smooth over here as you go to the BAO scale, which is now 150 megaparsecs. We changed over from H inverse megaparsecs. In contrast, the BAO scale in the with BAO model really has this pronounced bump. Now here I'm just showing 2 different ways of modeling this. One is a theoretical model that Daniel and I made, another is the industry standard numerical code. They basically agree. We understand why they don't agree. But the key point here is that this with BAO model has the bump and the no wiggle model does not have the bump. So the second piece that I need to give you is this alpha. Alpha is a contraction or dilation factor we apply to move the BAO out and in scale. So basically we just stretch or contract this plot here and move this bump in or out. And so we vary alpha, and by doing that, we can actually measure the size of the universe. So I'll just wrap up. we've made the first high significance BAO detection in the 3-point correlation function. This is showing you 2 different bias models that we fit, a minimal model and a model including tidal tensor biasing of galaxy formation. This chi-squared is just showing you how preferred the model with BAO is over the model without BAO. So the model with BAO is in blue. And you can see for both of these bias models, the BAO live in a roughly 4.5 sigma valley relative to the best fit model without BAO. So this is the first detection, and it's as expected. We've done this analysis for 300 Mach catalogs, and you can see that our chi-squared and delta chi-squared marked in red for the data and in blue for all the Machs is roughly in the range you'd expect given the survey size. So finally, given this high significance detection, we can actually use the 3-point function to measure the cosmic distance scale. So this left-hand plot is showing you our actual measurement of alpha, this distance scale. It's 1 if we had the correct cosmology already. So this is showing you our measurement of that for the data in red in the 300 Mach catalogs. And then here, this is actually the more interesting plot. It's showing you the error bars on alpha. For all of these, sigma alpha is the error. So you can actually see for the data, we're roughly achieving a 1.5% precision constraint on the cosmic distance scale. So to summarize, we've measured the distance to roughly 6 billion years in the universe's past. This is the number we find. And in detail, we ended up having a 1.7 precision percent constraint on the cosmic distance scale. And this is the first use of the BAO method in the 3-point function. And I think I should end on that. So this is just saying that you can actually use the 3-point function and the 2-point function in concert. Basically, the information in the 2 of them can be shown to be pretty much independent. So this is equivalent to adding an extra 1.5 years to BOSS for free. And this is just a more humorous calculation. So I'm taking the sandwich today as down payment on this.
So did you include the Keto price?
Well, no, I didn't know how much it was. So thank you. I think non-Gaussianity is expected to be a signal that's actually on even larger scales than the ones that I've shown you today. So I don't know if we've moved into the region yet where we can really probe primordial non-Gaussianity, but that is actually an analysis we're going to be looking into.
So as far as you're concerned, there is no additional information content in the report versus
Well, no, there is in the sense that the distance scale that you measure is independent. So if you measure a distance scale with 1% precision from both of them, then you can add those in quadrature and get down to, say, 0.8% precision on the combined result. There is also other information, which I didn't have time to discuss today, but basically you can constrain systematics that could systematically bias the distance scale inferred from the 2-point function, and that's another aspect of what we've done.
Computed the constraint that you're using for the dark energy using now 352?
I think basically we are actually finding that the distance scale we measure from the 3-point function is a little bit different from what we expected for this cosmology. Basically, if we had known the cosmology perfectly, we should recover that the distance scale was equal to 1 in the units that alpha has. So we're actually finding it's a little bit less than that, but I think it's only about 1% less than 1, so that's within the statistical error bar. So I don't think we've, from this analysis, found, oh, dark energy is very different from what we already thought it was. I don't think the constraint on the equation of state actually changes due to this. It just gets tighter in terms of error bars, but the center of the error bar doesn't move.
Last question. You said in the beginning that the dark energy is uniform. Do we really know that, and to what level?
Yeah, I don't think we really know that. I mean, it's a difficult test to make. I do think there are some constraints on that from the cosmic microwave background and probably also from lensing, but you basically need something that integrates over the entire volume. So since we're stuck sitting here, those are the only constraints that help us on that. But yeah, basically, I think the fairest thing to say is there's no reason we have at present to believe it's not uniform.
And with that positive note, let's thank
Ready? Okay. So I was inspired by Zach's talk about weddings and realized that 3 different men have asked me 3 different questions that changed my life, and 2 of them are in this room. So the first one is my husband, Garrett, for sure, and the question was, will you marry me? The second one is Leon Golub, who's also in the back in the middle, and he asked me to come to CFA to work on a rocket payload called Decode. And it was my first trip to CFA. And the rocket didn't get funded, but all the work we did ended up being some of the basis for the AIA instrument, which is based on the colloquium that I gave this morning. And the third one is actually relevant. It was from Don Niffen, who's at the time was the senior vice president for science at USRA. And he asked me, "You're not interested in the Arecibo job, are you?" And I think he was expecting me to say not just no, but hell no, because he knew of my history with Arecibo, which was so let's say unhappy. But that's not what today's talk is about. So I ended up applying for the job. I got the job, and now I'm the deputy director. And it's led to sort of a whirlwind reintroduction to what's going on in radio astronomy. And some of you may know that Arecibo had its 50th anniversary just a few years ago. And what I'm going to talk to you about today is the science, the radio astronomy that Arecibo has done in its second 50 years. But that's only 3 years, right, since 2013. So here's a smorgasbord of results. And the first one has to do with the Pleiades distance controversy. So any astronomer will tell you that distance is one of the hardest things to measure. Distances are bootstrapped from nearby objects to distant quasars. The Pleiades, this nearby cluster, sets the scale for a lot of other clusters. So a small error on the distance to Pleiades propagates, and it affects the size, the age, the physics of the universe, and the objects in the universe. So here is the result of trying to resolve the Pleiades distance controversy. And it's a plot from this Mellis et al. Paper where the distances are plotted with 1 sigma error bars. And all the black diamonds are ground-based. They're from traditional astronomy methods like isochron fitting and parallax, orbital modeling, and moving cluster. And you can see that a lot of the ground-based results have big error bars, but some of them have very tight error bars, and they sort of all agree. But the blue triangles are from Hipparchus, and Hipparchus was supposed to be the gold standard for distance measurements. And the distance to the Pleiades, according to Hipparchus, is significantly different than all the ground-based observations. So enter VLBI, and this is a result that some of the radio astronomers here will know quite well, that this VLBI measurement is of very weak radio stars in the Pleiades cluster. So because the radio stars are weak, you need the high sensitivity array. And Arecibo is an essential component of that high sensitivity array because of its enormous collecting area. that there's just no other game in town for, or at least not yet, for getting to being able to detect these very weak signals. And you can see that the red star with the error bar is the VLBI measurement. And it is completely consistent with all the ground-based observations and points the finger back at Hipparchus to say, what did you do wrong? So moving along, this is the big picture of gravitational waves. And Arecibo, unfortunately, didn't detect the first, but LIGO did. So starting on the right-hand side of this picture, in the high-frequency range, LIGO, the ground-based interferometers, they're detecting gravitational waves from things like neutron star or black hole binaries. If you move over to the left, to the low-frequency range, this is the range for space-based interferometers like LISA. And then moving further left in the very low frequency, this is where the domain of our Arecibo pulsar timing array. And we're looking for gravitational waves from supermassive black hole binaries. And then just to complete the picture in the extremely low range, this is the area of the cosmic microwave background and the place where BICEP 2 got into trouble for incomplete foreground subtraction. So with Arecibo, this is the regime of nanograv, which is the North American Nanohertz Observatory for Gravitational Waves. These gravitational waves cause the light travel time between objects to change. So the expected quadrupolar angular dependence, we're trying to detect that using an array of high precision millisecond pulsars, looking for variations in the pulse arrival time as a function of angle. So we're measuring strain produced as space-time warps. So here's the latest data release from 9 years of data from 2015. And it's the constraint on the gravitational wave strain on the y-axis as a function of frequency. And the colored bands are theoretical models for the strength of gravitational wave signature from supermassive black hole binaries. The different colors are different models. And the solid line is the data, which is getting better and better, so the constraints are moving lower and lower. And the solid line is if the upper limit, if frequency is just allowed to vary independently. And the dash line is if frequency varies with an expected spectral behavior. And just in case you don't know, this little peak here, that's the frequency associated with 1 year. So it's really hard to pin that down because of the orbital period of the Earth. So in this regime, the data are already starting to constrain the models. And if the universe behaves as expected, we are expecting to detect gravitational waves from this method within, say, 5 to 10 years. And if they don't detect them, then the universe is even more interesting. Right? Okay. So switching gears again, this is interstellar hydrogen. And it is, it's got an acronym, GALPHA, the Galactic Arecibo L-band feed array. So this is interstellar hydrogen at 20.1 centimeters. And it's a comparison between old data and Arecibo data. So on the top, you see data from LAB. LAB is with small telescopes. The L is Leiden, which did the northern hemisphere. A is Argentina, which did the southern. And B is Bonn, where they put the data together. But you can see that these filamentary structures are not even visible in the top panel, and they're only detectable with Arecibo's high spatial and spectral dynamic range. And the different colors are different velocity bands. So this is all relatively low velocity gas. And this is a close-up of an image. And there's a phenomenal video online from Josh Peak about the data from the survey. And this is interstellar. So this is hydrogen between the stars. And just think about, say, for hundreds of years, we thought that space between the stars was empty. And for decades, we thought it was simple, like it was magnetic, or it was gravitationally bound clouds, say, suspended in a warmer medium. And now we look at this and we say, it's not simple, it's complex, And I'm just going to describe it as magnetically mesmerizing for reasons that you see in this next picture. So the blue on the top is this Galpha H1 data that you just saw. And the orange on the bottom is the orientation of the magnetic field from Planck observations from polarized dust. And there's little white pseudovectors in there from the orientation of the magnetic field due to polarized starlight. So these filamentary structures in neutral hydrogen appear to be the result of magnetic fields between the stars. And then I just saved the best for last. In the March 3rd issue of Nature, it was the first repeating fast radio burst. And this was the art that the team submitted to try and vie for the cover of Nature. They didn't win. We never win. And they put some boring, medical thing on the cover as usual. But we think our art is a lot prettier. And these fast radio bursts are astronomical. They have millisecond duration radio pulses. They appear to be extragalactic because of the distribution and the dispersion measures. They have some unknown astrophysical origin. There are only 16 to date that have been reported, and this is the first ever repeater. And because it's a repeater, oh no, I'm done already, it demonstrates that the source survives the energetic event that caused the burst, and it rules out a complete set of models that require the catastrophic explosions. And this is the last one. So some of you that follow this will know that in the issue before March 3rd, there was another paper on fast radio bursts about the origin that was associated with a galaxy, with a galaxy. And we found out that that's not true. So that result was only a week old and they found out it was false. We know that our result isn't going to go that way because of dispersion measure. Not only do we have these pulses that are in the same location, but they also have the same dispersion measure, so they are unambiguously identifies the source as repeating. Thank you.
Thank you, Joan. Wonderful science. Question I wanted to ask you is, all of us are aware of the fact that NSF was contemplating reduced funding in the future. Is there any way we can help, or what do you see as the future funding plan?
Yes. Oh, sorry. I put the microphone down. Yes. So this has been an ongoing thing about what is the future of Arecibo. From the science perspective, we see it as bright, and we are still trying to learn what NSF intends to do. Our current cooperative agreement ends at the end of September. There has been lots and lots of talk from NSF that they're going to do an extension of that cooperative agreement, hopefully at the same funding level. But there's been nothing in writing. At the end of last year, NSF issued a Dear Colleague letter, which we responded to say, what is your vision for the future of Arecibo? And as far as I know, NSF has not let any of their thoughts on that leak, including to us. A third of our funding comes from NASA Planetary to do near-Earth asteroid observations and try and detect potential hazards. And that funding is stable. I'm told NSF Astronomy wants to continue, but we're not sure about NSF Aeronomy, and each of them give us a third funding. So there are lots of moving pieces. There's lots of uncertainty. But as far as the staff and the science goes, the staff is phenomenal, and the science is really interesting. I've had this crash course in science, in radio astronomy, or trying to reconnect with radio astronomy after doing solar physics for 20 years. And to me, it's so interesting what they're doing, and it's a great variety of things. So we hope that Arecibo has a bright future. I used to work at NSF right before I went to Arecibo, and NSF lawyers put a restraint on their past employees that for me, for 1 year, I can't talk to anyone at NSF. But those post-employment restrictions end in less than a month. And one of the things I'd really like to do is, invite our NSF program officer to celebrate the Arecibo's 100th anniversary, which of course is a while. We might all have trouble making it to that date, but it's just an indication that the staff and the scientists really think that Arecibo has a bright scientific future. We just hope we can convince NSF of that. Right.
I was just wondering whether you've heard anything from Gaia as far as their checking on the distance to the plate.
I haven't yet, but I'm hoping that Gaia comes down on our side, but but you never know. So, but
Using the same algorithms that Barcos used.
right. So, but that is definitely, and I should also say that none of this is my science, right? This is all radio astronomy that's done by other people that I'm trying to summarize for you. So they get all the credit, but yes, that is definitely something we're interested in finding out. And this campaign isn't over. I mean, the Pleiades distance campaign continues in the fall when the Pleiades is well situated for observations at Arecibo. So hopefully we'll be getting more data, better data, and hopefully, and also that Gaia will look at this and tell us where they come down.
So FAST is coming online later this year.
Mm-hmm.
Are Arecibo scientists or engineers working with the Chinese to help FAST get going?
No. But it is true that back many years ago, under the operation, when Arecibo was operated by Cornell, Chinese did come and take photographs of absolutely everything on the site. And so it's not like they reinvented this technology, they just took it. Since we are funded in part by NASA, we have very strict restrictions on how much we can communicate with the Chinese. NSF doesn't care as much, but NASA cares a lot. So we absolutely don't want to jeopardize our NASA funding, so we have to be really careful of not violating their rules and the law.
You might mention that FAST doesn't have the same frequency coverage.
Right. So there's differences with FAST. Like, first of all, FAST won't be observing the ionosphere. I mean, a third of our science is to study the ionosphere, and a third of our science is this planetary radar that observes not just asteroids, but anything in the inner solar system, and that FAST will not have that component. So 2/3 of our science FAST won't be doing, and we suspect that U.S. astronomers. So we don't expect FAST to have an open skies policy either. So we'll see. It's another interesting aspect. There are many interesting aspects of working at Arecibo. And there are a lot of moving pieces. So we just hope that they all move in the right direction. And then we'll continue. But stay tuned, because I don't know the answer either.
Okay, great. Hi, everybody. I'm here to tell you about Starshade Rendezvous. Starshade, as I'm going to explain to you, is a giant specially shaped screen that will block out starlight so the telescope sees the planet directly. My team, Starshade, wants to see a Starshade fly with the WFIRST mission, a 2.4-meter telescope that's supposed to launch sometime next decade. And the goal actually that we have is that every space telescope will be launched Starshade ready. That means it would have a way to communicate with the Starshade to be able to see the Starshade will have a big LED bank, a laser, and it'll have light leakage around the red for alignment. And the right camera, of course. Now here, I know everyone has their favorite exoplanet types. Hopefully that's true for the cosmologists as well. And we actually here are talking about Earth's analogs, Earth-sized planets orbiting nearby sun-like stars. And I'll remind you that our Earth in reflected light is only 10 billion times fainter than our sun. So when we talk about searching for Earth's directly in visible wavelengths, we need to suppress the starlight to 1 part in 10 billion. Now, I just have to flash up the team, and it reminds me to tell you, we were basically like a 2-year study group, but we weren't just like a paper pushing exercise. We had a real team of engineers listed here who solved a bunch of technical problems for us. And we actually ended up with a 200-page report, but if you go and look for it, you can just read the 4-page executive summary, and you'll get what you need. So here's an animation of Starshade. And by the way, the term Starshade Rendezvous means that Starshade would launch separately from whichever space telescope we're talking about, and it would meet up on orbit. So in this case, out at L2 with WFIRST. But this animation actually shows something different. It shows the Starshade and telescope launching together, and they would separate where the Starshade petals unfurl from their stowed position. This inner truss would actually expand, and the petals go in the second stage of deployment, snapping into place. These petals have to be very carefully manufactured. The precision in the shape has to be to hundreds of microns. And the petals themselves have to deploy with respect to each other to millimeters. There's a pretty tight error budget, but everything's measured in in microns, millimeters, meters, etc. Now the Starshade eventually would, as I said, block out starlight so we could see planets directly. And oddly enough, in this animation, there's a Jupiter and an Earth. The special shape, by the way, is due to diffracted light. We can't put like a big circular screen or square screen because diffraction means that screen would have to be so big that it would be completely impractical. And if you had time to work out the math, you would see that the Starshade actually has to be tens of meters in diameter, and it has to fly tens of thousands of kilometers from the telescope. And the tolerances are very tight. There's no easy way to find an Earth twin, unfortunately. We can talk more about the error budget and tolerances later. But in this diagram, we're showing you a cartoon diagram of a telescope. Again, we imagine AFTA WFIRST separated with the Starshade, not to scale, obviously. And there's one main point I want you to, if you can only remember one thing in this talk, what I want you to remember is that the Starshade does all of the hard work of suppressing starlight, and that includes spatially separating the planet and star on the sky. So we all learned in Astronomy 101 that it's our mirror diameter that really matters. That lambda over d, that's, separates the planet and star. And in this case, no, that's not it. It's actually just the Starshade itself. So just theoretically, I know there's a lot of theorists here, it's ITC, you could have like a 1 centimeter telescope with the right Starshade. But in practice, that doesn't work because you have integration time and there's a PSF and there's a lot of other complicating factors. And we think that 2.4 meters is the minimum, about the minimum size actually, to be able to search for Earths around the nearest few dozen sun-like stars. I just want to make one more point because people often ask about the chronograph, which blocks light on the inside of the telescope. And I want you to know that for the same size mirror, the chronograph cannot reach down to Earth's. And the reason is simply wavefront control. You know how here on Earth, on the large ground-based telescopes, we use laser guide stars so we can get enough information to pass through the telescope to do correction. Well, the sun-like stars accessible to the 2.4 meter just aren't bright enough to give enough information to beat down the noise involved to be able to do that starlight suppression. So the reason I like the Starshade is because it's our first chance, assuming we can find a way strategically and politically to be launched and to be able to go with WFIRST, that we can actually find Earths. And so I don't want to overpromise because as hard as it sounds, here's what our simulated image would look like. This is credited to Mark Kuchner. And up on the left there, it says what type of star and how far away it is and everything. What you see here, the easiest thing to see is Jupiter. And here would be Saturn. This dust ring is actually a fake Kuiper belt that's brighter and closer in, just for illustration purposes. By the way, based on Hubble Deep Field and Ultra Deep Field, we know there'd be at least some background galaxies for contamination that would be contaminating our image. Now, where's Earth? It's right inside there. And it's the zodiacal dust that at least our solar system has from our asteroid belt that's a major killer to this problem. And in fact, it kind of remains one of those big unknowns out there, that if all planetary systems have asteroid belts bigger than ours, more massive than ours, this dust will be a real problem for any technique that wants to directly image Earths. Actually, it looks a lot worse on this screen than on here, just FYI. So in terms of what we can do for spectra, I know this is going to read, this is based on a report to NASA, so it's a little bit political, but I just want you to look at the spectrum on the left because it shows you for different planet types what we would be getting for planets. And these planets actually do range from a Jupiter through these so-called sub-Neptunes, super-Earths, and down Earth is at the very bottom. And there's wavelength at the bottom, which shows you that this telescope Starshade and with WFIRST, or any telescope, if designed properly, would be able to get us from about 0.4 out to 1 microns. So what you see at a glance, I bet if you look at it just like quickly, they all look the same, right? All the spectra look similar. And that's mostly because water vapor and methane are the dominant gases at the temperatures of planets of interest. But you'd have to spend more time looking at this closely to see what you could pull out. Mostly we want to see water vapor and oxygen and Rayleigh scattering. Now the main downside of the starshade is every single time that you want to move to a new target star, the starshade has to move across the sky, or the telescope does. And this is tough, actually. It could take a week, it could take 2 weeks, and fuel basically, and time actually is the limiting problem. So we actually just, and many people have worked on this, show like a proof of concept that we actually can survey enough stars given all the mass and fuel constraints and everything. This is showing you ecliptic longitude at the bottom and ecliptic latitude on the y-axis. And it shows you, like, number one is where we would start our sort of hypothetical proof of concept observing sequence. And this sequence actually is anchored with the diamonds, which are, the red circles, which are known Jupiters. We'd want to be able to move around the sky and make sure we hit those known Jupiters for guaranteed science return because we know they're there. All the other stars are actually chosen just for searches, blind searches, and Earth's would be the next priority, stars that are near enough that we can block out the starlight and see the Earth. So all this just shows you, as you imagine you're moving in the sequence, the starshade across the sky in this optimized way. And it's just supposed to convince you that we can look at enough stars, in principle. So now I'm going to tell you two more things in my short presentation. So the starshade is so huge and it's so big, and how do you test this? Well, it turns out we can't actually test it without building the real thing. And so for the moment, two separate things happen. The first one is we is not me, but it's the community of starshade people, test the starshade either in the lab, and at Princeton they're building like a 100 meter or 200 meter long kind of tunnel. It's like an above ground kind of fiberglass tunnel, and making a tiny starshade. And here is Northrop Grumman actually does testing in the desert. And this is showing you their camera, a fake LED, and they put the starshade in the middle, where this whole distance is 3 or 4 kilometers. They've also done testing on the McMath Solar Observatory, and believe it or not, they've blocked out bright stars like Vega, and they've seen stars that we have never mapped before. Now, where we're doing this is for optical model validation. Does the math work like we expect? If we put defects on the starshade, are we getting what we expect out? And initially, like all the people who modeled it, just like a lot of modelers, it didn't agree, but it's starting to agree now. And they haven't been able to reach down to either the right, what we call Fresnel number, or contrast, but they're working on it. The second thing in parallel to optical model validation is making the starshade at full scale. And here's another video, now this is quite old, from a few years ago, showing you the starshade petal stowage and deployment. These petals this is like a real-time video now, and this was done at Northrop Grumman Astor Aerospace in California. They only made 4 because it's all they could afford. But they're testing the petals to show that they can deploy. And it's going to switch in a moment to a time-lapse position to show you the second stage of deployment. And here you'll see I always get asked, where are there people here? Because there won't be people in space. But the test actually, now they can do it automatically, but the test is to show that doing this over and over again for 25 or more times, the petals will unfurl to the right position with respect to each other to within centimeters. And they were successful. There's more versions of the starshade. Here's a new one at JPL. One thing about this is you get a lot of cool pictures. Here's myself and two of the team members with, look at that petal. That petal is big and it looks dangerous. And it's because, a sort of little aside is that people have thought about the starshade for a long time, since Spitzer himself in the 1960s, and each decade it's been revisited. But initially they conceived that you'd have to actually have an apodized screen. But that apodization is too tough, so mathematically equivalent, and there's different families of solution, is this special petal shaped with the very long tips. I'm almost finished, actually. I just wanted you to see some other cool pictures in the Starshade lab. And last time I was there, I got a little souvenir about how the optical shield will stow and deploy. It's just this little piece of origami paper. And that's actually how that works. There's a little video on YouTube you can look up now. I'm just going to finish with what is a bit of a political thing, but I want you to see this chart of 20 meter, 34 meter, 40 meter starshade. The team sort of closed out our study with this concept of, depending on the starshade size, you get different capability, actually. And so there's a range of options, and this would range from like 300 million to 800 million, depending on what size and what capability you'd like. So I'm going to finish there. And thanks for your attention. It's a good question. People have talked about this, about putting lasers maybe out on a truss somewhere that point back and let it light up, but I'm not sure why they haven't adopted that concept. But I just want to say that in our ultimate greediness as scientists, we'd like to have a telescope that has both a chronograph and a starshade, so the chronograph can quickly search for planets and the starshade can move in place to get broadband spectra.
I didn't notice Alpha Centauri on your stars.
Would you like to get your computer started? Yeah, Alpha Centauri, definitely one of our favorite stars. It's kind of sad that, there's that phrase, most stars are binaries, and Alpha Centauri makes a really big problem for starlight suppression. We think that with pretty much every technique for starlight suppression, you can do Alpha Centauri, only it requires like a unique setup. So you might have to create a very special starshade, you could create a very special starlight suppression, but it will probably only work for Alpha Centauri. And many people want to imagine like a mission. I'll just say one more thing while we're waiting for the next talk. Okay, right. I just have this really interesting point that there's been this like movement lately to consider, well, maybe we should just study Alpha Centauri, only Alpha Centauri, and spend like 100 million or 200 million just studying that star. And Avi is involved with the Breakthrough Foundation. I've been peripherally involved, and others actually through NASA studies have all been discussing this option. So we may go to this kind of very expensive way of looking for Earths, but that might be what we end up with.
I just had a question about the station keeping challenge for the Starshade. Is that something that's been achieved already, or is that based on design projections?
Okay, so that's one of our, let's say 5 tall poles is how to do this formation flying. Because no one fortunately asked me. You guys are a lot, so you're being an easy audience so far. But in formation flying, this thing has to be aligned in vertical directions. Remember, it's tens of thousands of kilometers. It has about hundreds of kilometers. But side to side, depending on if you want your starshade to be really as small as efficient, that's only meters. That's an incredible challenge. And the team has worked out how they will do this. But to answer your question more directly, the team worked out which part of parameter space is left based on what we have done so far, although we have not obviously tested anything at tens of thousands of kilometers. We have things that have happened in our own Earth's gravity. There have been some small formation flying demos. We dock at the space station in Earth's gravity, which is tricky. The mission Grail, which were these 2 laser ranging spacecraft that orbited the moon. And if you were to work out all the things we have done, then you get left with what you need to work on and demonstrate so far. I'm not saying by any means it's easy. I'm just saying that some parts of the problem have been solved. And what was surprising to me is what they end up saying is that, people think they can handle the algorithms, but the biggest challenge actually is sensing. Because the starshade is so far away, and although it has an LED bank for initial, tracking and then a laser, how you can track on that kind of spread out beam so far away, that's the main problem that they're facing right now, that people are working on that problem in the lab.
Detecting an Earth with a 2.4 meter telescope is challenging. You don't get a lot of photons, so when you divide that by the resolving power, it becomes even more challenging. How much integration time does it take to build up sigma, 5 at least spectrum of an Earth analog around one of these nearby stars?
Great question, Gary. And just first to answer that, trust me, we'd rather have a much bigger telescope. We hear you. It's almost hard. Anywhere from a day from the brightest star to a week or more for the fainter ones. So it's a long time, but it's not months. It's still a very long time.
And does the orientation of the zodiacal dust in the system, is that critical? I can imagine if you're near edge on, that complicates things considerably.
Yes, definitely matters. And just as one final comment is that we'd like to be able to assess the zodiac in advance, but that's tricky to do from here. So, thank you.
Okay, so switching gears again. Okay. All right, so I gave a talk, I don't remember, it was maybe a year and a half ago, summarizing this discovery, but I wanted to remind you what it was and some of the advances we have done since then. So, again, the slides you probably remember from last time, but I thought it would be good to introduce. Where's my laser pointer here? Huh? Okay, this is better. Anyway, so as we look at beautiful images from HST, from Spitzer, we know that stars, a lot of them have winds, and they create these bubbles called astrospheres or heliosphere as they move through the interstellar medium. And so this is some of the images, and you see these beautiful long comets. And again, this is a picture, maybe it's a good follow-up to what Sara was talking. We were trying to discover planets around other stars, and here I pointed out for this from Seth Redfield picture, some of the stars nearby that we know that have astrospheres that indirectly we had detected. Those winds are very rarefied, so it's really hard to detect the wind directly, and the astrospheres are not all pointing in the same direction, but those are at least showing that we know that they have a bubble around them. So the conditions around planets will depend on how much these astrospheres can filter dust, for example, around these stars. So it's this slide is basically to emphasize the importance for us to understand the physics of astrospheres. This is basically the filter that separates the star from the rest of the interstellar medium. So the best example we have is our own bubble, the Heliosphere. This is a new cartoon from NASA when showing the two spacecraft still alive, Voyager 1 and 2, that are measuring the properties of this astrosphere. One is outside our heliosphere, and the other one it will leave in the next couple of years. But the main point here that the typical picture that we have for a heliosphere or for a bubble around any other star, that as the star moves through the interstellar medium, the wind from the star gets deflected back and forms this long tail, a comet-shaped tail. So this is a standard paradigm. It's going on for years, and the main idea come from Parker in 1961. That, and summarizing our own bubble here, there's a lot of detail. I won't enter into it, but again, this is a nose as we go through the interstellar medium, and there is a wall that separates us from the rest of the interstellar medium that we call the heliopause. This is where the pressure from the solar wind is separated from the outside. And what you need to keep in mind that anything inside the heliopause is mediated by the wind from the sun, and anything outside is the interstellar medium. And the two of them don't communicate. This is plasma, right? Ionized matter don't communicate. So it's important to know what the heliopause is, what the shape of it, how it's let some filter, some dust or not. But in this typical cartoon, the magnetic field of the sun doesn't play a role. So the idea that's going on since Parker, and there is a Russian group by Baranov, that you have a magnetic field from the sun, in this case, it's a typical magnetic field that any other star will have, radial, and as the star rotates, you will have a big tornado, a big toroidal component shown in yellow. And because the wind gets deflected to the tail, the tornado gets deflected to the tail. So there is no assumptions here. You have the toroidal get deflected and get stretched back to this long tail. So what we discovered last year, this was a big surprise, that the heliosphere does not look like a long comet shape, but have this, what I like to call croissant heliosphere, for obvious reasons. In the last meeting, I got a prize for the best gourmet talk based on the shape. And here, what you can see, this is an interstellar magnetic field, the red lines wrapping around our own bubble that is shown in yellow. And what is organizing this magnetic this yellow shape is a magnetic field of the sun. And it's a big surprise. The magnetic field of the sun here is showing in these gray lines. And you can think that this is a backbone. This is a skeleton of the heliosphere, is the solar magnetic field. It's a big, big surprise because when you think about the pressures, the back of the envelope calculations, the thermal pressure outside here is much, much, much higher than the magnetic pressure. So you will think in first approximation that the magnetic field will not play a role. And what we stumble into it and we try to understand and we summarize the results in these two papers. But what we found out, and I just will show you one slide to convince you, that the sun drive flows here. It's not just the shape of a cross-sun, but the sun really drive jets here. And it's not just a name we're using, jet, because we're using that because the wind that gets accelerated here is not just a solar wind get deflected to the north, but it gets accelerated by the magnetic field. So it's a mechanism of acceleration and collimation as a jet. So my colleague Jim Drake liked to call it heliosphere with jets instead of the cross-sun. But so here is one slide to convince you. We have more analytic work, but the main crux is when you try to think about a magnetic field that is a loop going down the tail, those flows that are going down the tail are subsonic, are very slow. So you're trying to stretch that field line. What really matter is not the isotropic pressure, that is the thermal, but is the flow stretching. And so you really need to compare the flows pressure versus the magnetic tension. And when you put this calculation together, I'm going to go quick on that. The stretching force over the tension is related to the ramp pressure of the magnetic pressure. The thermal pressure doesn't play a role here. So if the magnetic pressure is dominant over the flows, if you have a very slow flows, the magnetic field will be the one to dominate the whole structure. And if you look in the literature, this is what we found out. The jets that are driven from the Crab Nebula have exactly the same mechanism. They're driven by the flows, the slow flows in the sheath around the nebula, very much like the solar jets. And there is another physical idea that I want you guys to keep in mind. The full analytic work we have in this paper here. And I want you to pay attention to this equation. If you look, this is analytic work, and this is from an MHD solution that I did, that the pressure down the termination shock, and termination shock is where the wind becomes subsonic, that is getting to the heliopause, the last boundary that is here. And look at these profiles. The thermal pressure that is in dashed line is order of magnitude higher than the magnetic pressure. So this is why Parker and others had neglected the magnetic pressure, saying, really what is dominant is the thermal pressure in the sheath. But you can see that in the analytic work, the drop between the pressure and the termination shock to the interstellar medium, this drop, is dominated by the ratio of the flows versus the Alfvén speed. So this drop in the pressure is given by the tension. You can think like two major players. Thermal pressure is pushing against the interstellar pressure, and really what you have is a little David, not the Goliath, a little David, the flows that are fighting against the magnetic tension. And so that magnetic tension, that drop, is what is going to drive the jets. So you can derive that the flows along the jet are driven by this drop in a gradient in pressure. So it's a driven mechanism. And again, I'm emphasizing this is even in a high beta, when the magnetic pressure is not dominant. Okay, so what we found, this is a cut of our heliosphere, that we don't have a long tail. The distance to the nose is equivalent to the tail. And then you have these two jets that have enormous turbulence. And they have lots of instabilities. One of the reasons, because we don't have an axial field to stabilize it. So you have kink instabilities, you have sausage instabilities, and you also have reconnection between interstellar magnetic field and solar driving it. And again, I just wanted to emphasize, maybe most of stars will have something similar. If stars are moving through the interstellar medium, there is no reason why they will drive a jet very, very similar to what the sun is doing. There's nothing spectacular why the sun is doing it. We think this is the largest turbulent. This is the lab of the largest turbulence in the heliosphere. And although those are in very large scales, we expect this to cascade to smaller scales and smaller time scales. So what exactly is going to do for the interstellar medium, for acceleration of particles around stars, we don't know. And I'm running out of time, so I'm just going to, can I do 1 more minute? To show you, one of the things we have done recently is to try to understand why the magnetic field outside the heliosphere, this is data from Voyager, this is outside the heliosphere, and if you look at the angles outside the heliosphere, the solar magnetic field, the magnetic field outside the heliosphere is solar. It's very weird. We left the solar system, but the magnetic field from the ISM is solar. And this led the Voyager team not to believe that we left the heliosphere. So this has been a big, big debate. So what I want to leave you with, this is what we published in 2013, and now we understand what's going on. The draping of the interstellar magnetic field is completely dominated by this short tail, by these two jets. The interstellar magnetic field wrap around and reconnect in the back and make this whole twist from the interstellar magnetic field being very inclined to be solar-like. Again, I think it's a pretty universal effect for other stars as well. I will stop here.
One question over there.
Isn't the MHD model will over-reconnect, so this effect will intensify maybe more than in reality?
Yes, yes. And so we are investigating how much we think, if I didn't show you this slide, as you wrap around, you have a large region between these two jets when you can have reconnection. So we are doing more detailed particle in cell simulation to really pinpoint where we expect physically this to happen. The MHD won't give you that. But this is a perfect location because it's so short where you will have enough anti-parallel field for this to happen.
So Merav will be around, and if people would like to discuss more with her, that's the last ITC lunch this semester. Have a wonderful summer. And see you very next
Every time I get it, I get a pleasure. Okay.